this is the last installment, AF sensors. We're going to cover a little bit of O2 sensor just in the very beginning, because O2 sensors are also an integral portion of an AF sensor. And if you didn't know that we had dual AFs on the A25A and the M20A, you will now. We didn't actually know after we went to a 3-day training out in Plano in fall of 2018, and it was all Camry new model with the A25A. We adjusted cameras and all kinds of stuff, and we got back here and Dale was going to try to use one of the 18 Camrys in class and one of the engine controls class, and found out that it had a rear AF sensor. Because it wasn't a new component in the vehicle, Plano didn't think that it was worthy of a new model talk, I guess. So we're going to concentrate on that towards the end of the program, because it is a different way to look at stuff. All right, so we'll get going. All right, so just a quick review. We've got 2 sets of sensors, bank 1, sensor 1, bank 1, sensor 2. Of course, we're using an AF sensor, and then a rear O2 still on the 2GR FKS. And then we've got bank 1, sensor 1, AF sensor, and then bank 1, sensor 2, a rear O2 also on the 2GR FKS. So that is still a traditional layout that we've been doing it for the last 18 years, something like that, because early 2000s, mid 2000s, we introduced forward AF, and it was a big secret and all that stuff. All right, so let's take a look at an oxygen sensor. So within an oxygen sensor, we've got a heater circuit on the inside. The heater is really important with that. And then if we come over a little bit farther, I've got my exhaust stream right here. And in the exhaust stream, I have something about 0.5% of oxygen left in the exhaust stream. And then of course, everybody always forgets, but on the top part of the sensor where these couple little holes are, we're sensing what outside oxygen is. And somewhere between 18–20% in the atmosphere is the oxygen level. And that's kind of our electrolyte for the sensor. So I have 0.5% roughly in the exhaust stream, 20% sensing up here. I've got the zirconia element with the 2 platinum electrodes, and the oxygen is basically my electrolyte. And with the zirconia element and a chemical change, we're basically moving electrons and we're making a voltage. So if you guys remember, with the voltage, when we're at stoichiometric or middle, we're at about 0.5 volt, 0.45, 0.4 volts on an oxygen sensor. One of the things about an oxygen sensor, I need my prop here, is they call it a narrowband sensor. And the reason for that, if you look at this band here on this chart, it knows stoichiometric here in the middle. That's my 0.4, 0.45 volts. And then once I go rich, it doesn't really know how rich I am. And then once it drops down and goes lean, it doesn't really know how lean it is. So it's kind of like if I'm the engine and I go lean and I want to add some fuel with fuel trims. I got my cup right here. Oxygen sensor, I'm just going to take a big swig. And I've added that fuel. Now, of course, I'm not going to spit it out on the carpet if I was going to remove some fuel, but I don't really know how much fuel I'm kind of adding and taking away, so it's kind of always searching back and forth. If I hit my stoichiometric here in the middle and I go rich a little bit and voltage goes up, I take some fuel away. I get back to the center a little bit. Oh, I take a little too much fuel away, and it's constantly sweeping back and forth. It's not a bad way to manage fuel, but it's not all that accurate. So I got my chart right here, and we'll do a quick review. All right, so hoping you guys can see the whiteboard. I kind of laid it out up top here. So I'm always looking for stoichiometric. My 14.7 pounds of air to 1 pound of fuel is the ideal mixture that we can do in an internal combustion engine. I have my narrowband sensor up here. And remember, when we go rich, we are low on oxygen. I learned rich lean on carburetors years ago, and it was when you were rich, you had too much fuel, which we still kind of do here, but we're looking at the exhaust stream. We're not measuring hydrocarbons, we're measuring oxygen in the exhaust stream. When I go lean, I'm high on oxygen, which means I'm low on fuel. All right, so let's take a look at it. So at stoichiometric, I'm going to go with 0.45 volts. Roughly 0.5 volt, somewhere in that range. That's my good range. That's where I want to be. When I go lean, and I'm high on oxygen, of course, the voltage values go which way? Anybody remember? Voltage values go down. So I'm looking at 0.1 volt. I've seen it even lower than that. And if we think about the chart in the previous slide, it kind of knew after I left 14.7, it didn't know if I was 17 to 1, 18, 19 to 1. I don't really know what those voltages are or what my air-fuel ratio is. So now when I go rich, and I'm looking at it over here, when I go rich, my voltage values, even though I'm low on O2, my voltage values go up. And I'm looking at 0.8, 0.9 volts, something like that for the oxygen sensor. But again, it doesn't really know how rich I am. It's kind of like your wallet, your bank account. You're pretty rich right after payday, and then how quickly does it go lean, right? So that is narrowband oxygen sensor. And we'll kind of keep that in mind when we get into the next stuff on the AF sensor. All right, so we'll leave that off the frame. Throw these up here so I can lose those later. And then one of the most important parts of any of the AFs or the O2s is the heater. Back in the old days, there was no heater circuit, so we had a single wire voltage coming out of an O2 sensor, and you had to drive around a lot to get it up to 700 degrees because there was no heater. So it took a really long time to go into closed loop, because the oxygen sensor operates best at about 700 degrees Fahrenheit. So we have the heater circuit right here. Notice it works off of an EFI main fuse. And then also I've got its own relay, or in this case it's running off of the EFI main relay too as well. And then up inside the ECM I have a transistor that's turning on and off. So let's take a look at what we got going on here. So some circuit notes. The amperage load is about 2 amps, so it's not that high an amperage load, which is why it can share components. It requires 700 degrees. The ECM basically cycles that transistor on and off in about 1/10 of a second or 100 milliseconds until the maximum exhaust temperature is reached. Now years ago in AFs and O2s, I thought there was some kind of cool thermistor or something like that inside the O2 sensor or something in the exhaust, and it's not. Basically the ECM, based on calculated load, actual load, fuel trims, all that stuff and everything, it figures out what the exhaust temperature is, and then it'll taper off the heater. And then of course with an AF, it'll turn on and off. We'll get into that too as well. So again, low amperage draw. If I have to diagnose it, it's normally a problem with what? If you have a problem with an O2 sensor and even AF sensor, what usually goes bad? Heater circuit, right? It's living in a really tough environment. You got a resistor inside the element of the sensor. So basically what do? You throw a sensor in it, and 95% of the time it does what? Fixes it, right? And I'm good to go. And then you only need to usually look at the circuit when? When you put that sensor in, it needed it anyway because it was not working right, and then you got to diagnose the circuit. So that's why we're covering a little bit of the circuit too as well. All right, next is AF sensor. An AF sensor is called a wideband sensor. And if we look just back to my chart here behind me, you can see how stoichiometric is right about here where my right hand is. And then you'll notice I have a gentle curve going down to rich, and then also a curve going up to lean. So it kind of knows, in between what's rich and what's lean. So if I go back to my fuel, so instead of taking a big gulp out of this, the AF sensor knows pretty much how rich or lean it's gone, and it knows how much fuel to add, so I can get a little bit more precise reading, and I can adjust my fuel trims accordingly, which is why we've used forward AF since about mid-2000s. All right, so if you'll notice, I still have exhaust stream. I'm looking at about 0.5% of oxygen, about 18 to 20 up top. If you were to lay these side by side, other than the number of wires even, I got 4 wires on an AF sensor. They look very similar in operation because I still have an oxygen sensor component to an AF sensor. And one of the cool things, we can see from my chart here, I've got a milliamps reading and a voltage reading, and I know again how rich or how lean I've gone. So bring this back into play. Look at that. I've covered up the chart, but we got this going on now. So again, with good, for Toyota's sake, good voltage on one of our AF sensors when we still had voltage as a parameter was 3.3 volts. If we ever looked at the FRS is actually 2.1 volts, that little bit of Subaru background. If anybody ever looked at a GM product or something like that, you're in that same range, about 2.25 volts is stoichiometric. What they did way back when we introduced AF sensors, technicians were already used to looking at voltage for diagnosis, so the ECM basically calculated this voltage value. The entire time it's looking at milliamps. Hell, we didn't even give you that as a parameter for the longest time. We just gave you the voltage because that's what you were looking at. All right, so let's look at what happens to voltage when we go lean. So I'm going to go lean. Again, that is low on oxygen. Now, or high on oxygen, the O2 sensor measured low. So of course we couldn't follow that. So an AF sensor, the voltage actually goes up. So for voltage, I'm looking at up. And again, I'm looking at probably around 4 volts. Pretty common for going lean. So the voltage went up. When I went rich, voltage went, if one went up, the other one's got to go down, right? So voltage goes down. I'll roll with, say, 2.4 volts down. So voltage goes up in an O2 sensor, down in an AF sensor, down in an O2 sensor, up in an AF sensor. But the real key, what it's looking at, is looking at milliamps. There's something called the pumping circuit on it, and we'll get into that in the next couple of slides. So if we're looking at milliamps, when I am not making any changes and I'm at my 3.3 volts, my milliamps are roughly somewhere around 0, plus or minus a little bit. When I go rich, my voltage goes up, and then also my amperage goes up. So my amperage we're going to look at, I'm going to say 0.45 milliamps, and that is a positive number. Now my voltage, when we had that as a parameter, that went down. My milliamp number is actually going to go down, and it's going to have a negative sign in front of it, and we'll pick 0.54 milliamps. And that's exactly the reading that the ECM is using to interpret what the air-fuel ratio is. So we'll move that, get that out of the way, and you can see by my chart here, some of those numbers I picked. I have 0.54 milliamps. That equates to 2.4 volts, and it knows I'm like 12-to-1 air-fuel ratio. That's very rich from 14.7. And if I come back over here and look at my 4 volts, I'm somewhere right around in here, and I'm roughly about 17-to-1, and my milliamp number is somewhere in that 0.35 to 0.4. Is that cool? So what we're looking at now, and the ECM is only looking at, it always did, if anybody's looked at parameter-wise, we've removed that voltage as a parameter on all the new stuff. All right, so let's look at what's happening inside the AF sensor. So you notice I had talked about 2 pumping circuits. I have AF plus, AF minus, and then you'll notice I have a little current detection ring in the ECM, and it's actually watching for current flow from one side to the other. Up here is my O2 portion of it. So you'll notice I have 2.9 volts on this side. I have 3.3 volts on that side. If I take 0.4 volts and add it to 2.9, tough math question of the day, what do you get? 3.3 volts. So if we go back to super basic electrical, if I have 3.3 volts on the AF minus side, 3.3 volts on the positive side, I don't have any differential in electrical pressure, so I flow no current. You'll notice that right above me here I have 0 milliamps, my 3.3 volts, and then I have a lambda of 1.4. We actually got rid of the lambda value too. We just give you a target lambda. When we actually had an actual lambda value, I could calculate what the air-fuel ratio was for the vehicle. Now we just give you a target, which is 1, which is stoichiometric, my 14.7 to 1 ratio. All right, so that's nothing going on. Everything's looking good in the exhaust stream. All right, next I've gone what direction here in my voltage? I've gone positive, plus it says the word lean right above my O2 sensor portion. So when I go lean in an O2 sensor, I'm going to go with 0.1 volts. If I add 0.1 to 2.9, I get 3 volts on the AF minus side. I have 3.3 volts on the other side. So I get current in what's considered the normal. So I'm going from positive to negative. So I will see a positive current flow. That's where I got that 0.4, 0.45 milliamps. And that's what the ECM is looking at. So that's lean. Now we'll take a look at rich. In rich, if I have 2.9 volts on this side, and let's say I had 0.8 on the O2 sensor portion of the AF sensor, 0.8 and 2.9 is 3.7 volts, so I have 3.7 on this side. I have only 3.3 on the other side, so I'm pushing current in the backwards direction, so that's why I have a negative current flow. The cool thing about all of these, if I have a negative current flow on the AF sensor, I know I'm too rich, and what am I going to take away on fuel trims? I'm going to take fuel away. If I go back to my lean, and I have a positive number, 0.36 in this case, I have too much oxygen, not enough fuel, so I'm going to add fuel. So that's the cool portion of this. If I have a negative number for milliamps, the ECM is going to take away fuel. If I have a positive number for milliamps, it's going to add fuel later on in fuel trims. All right, so the next part of this is the heater circuit. Now you will notice in this example I have a separate AF relay. There would be normally a separate AF fuse to go with it. So most of our 4-cylinder engines will have except for like the smaller diameter, smaller bore stuff, but like the 825A will have a AF sensor relay. It'll have a fuse, because I'm running, I'm running 8 to 10 amps on this heater circuit versus 2, because I want to hit 1200 degrees on an AF sensor. So the heater circuit is really important. You'll notice I also have a transistor in the ECM, and the difference is that instead of cycling it on and off in a certain interval, I'm going to basically, to hit that 1200 degrees, I have full duty cycle control of that transistor. I'm going to cycle it on and off anywhere from 100% on time to 0% on time, depending on the exhaust temperature. So the heater is even more important in an AF sensor, which is also what normally goes bad? The heater circuit. Do we ever really need to look at the circuit, even though it says it in the repair manual first? No, we usually do what? We throw a sensor at it, and then we're good to go, right? And 99% of the time, 95% of the time, we nail it. And then again, we normally have a dedicated fuse and relay, and most of our larger displacement engines, like a 3UR 5.7, that'll have a relay and a fuse for each bank, the 4-liter the same way. So V6s, we may use a separate, or we may use 2, depending on the displacement of the engine. All right, and then there's a cool comparison of a wideband sensor, the AF, versus my narrowband O2. This is a cool chart. I love it. All right, next, AF sensor diagnostics. So I know I'm preaching to the choir here. DTCs are always great. Data list is good, snapshots are good, graphing is good, monitor status is also good, especially if I want to know that I fixed it. Go for a test drive and see if the monitor runs and repopulates. And then my favorite test while I'm in there checking codes, and I'll even do this during a lean condition check, I'll look for the active test, and it's control the injector volume for AF sensor. Gives you a nice little data list and stuff and everything. That is a great active test to see if I can get either the forward AF, rear O2, forward AF, or rear AF to move when I swing the fuel rich and lean. So this test basically takes away 12.5% of fuel, It has a 0 setting, and then I can add 12.5% fuel as well. This is one of the things you guys are going to do on the worksheet. All right, so some data list changes. Those of you that were looking at stuff in 2018, all of a sudden you found out that the voltage that we used for a long time was gone, and we strictly have milliamp now. So the only data list parameter is the milliamp. The cool thing is that milliamp number is what the ECM is looking at and making calculations off of. Actual lambda, no longer a value, but we have a target lambda, which is always 1. Somewhere around 1. You'll see like 0.99, 1.00 something and change. And then the other point on that too is bank 1, sensor 1, especially when I'm running, bank 1, sensor 2, especially when I'm running a second AF, it'll update in several seconds, a few seconds, but up to 20 seconds it says in the repair manual. So you have to be a little patient when you're swinging rich lean and looking for a reaction out of a rear AF. All right, next. So when you look at the repair manual, this is for an A25A out of a Camry. You'll notice all of a sudden there are 2 AF sensors, which, like I said, we didn't even know after 3 days of intensive training. But it is there. All right, so one of the reasons that we do it. Obviously, a rear AF provides a more accurate reading. We had always heard that we never really got a solid number from Toyota, but even a rear O2 did a small percentage of fuel trim calculations. What's great about a rear O2, a rear AF, I mean, is think about the accuracy when I'm running a CAT monitor and I'm swinging it rich lean, and what kind of readings I get for that oxygen storage capacity now out of an AF sensor. We couldn't find an actual number on it, and Scott did quite a bit of research. All we know is the rear AF does a little bit more fuel control than it ever did when it was a rear O2. And let's look at some numbers. So bank 1, sensor 1 looks pretty normal. When I go rich, notice I have a negative milliamp. When I go lean, I have a positive milliamp number. And then notice here, whoa, wait a minute. Bank 1, sensor 2, that's actually 8 milliamps. That's not tenths, hundredths of a milliamp, that's 8 milliamps. The range for the forward one is basically half a milliamp negative to about half a milliamp positive. On the rear, it's actually minus or a negative 10 milliamps up to a positive 10 milliamps. We notice that when it goes lean, it's kind of a direct correlation. These numbers are a little bit different, but I've checked these, and let's say I had 0.25 milliamps when I went lean, I'd actually have 2.5 milliamps when I went rich. So there is a significant difference in the readings. We asked, and right now, let me see, we're on about 1.5 years. And just accept that, it is, and that's the way they read. We didn't really get any engineering stuff or background on why they read so differently informationally wise. So I got the highlights right here, that half and then 10 milliamps on the slide too as well. All right, so also, this is what it would look like graphed out, and here's my negative 8.08 milliamps, and then you can see my positive milliamps there. You can see my injector volume. I was swinging it rich. I was adding 12.5% fuel with that active test. And then you can see where my CAT judgment took place between the red arrows there and stuff. And next, Scott should have sent you guys out a worksheet. Hopefully you can get it done. I know tomorrow's Friday. I promise you the worksheet, it's only one, and it's not as long as the EVAP one. So if you could at least take a look at it, play around with it, be cool, and we'll go over it tomorrow at 2 o'clock.